In this video, we're going to look at the idea of a complex number or complex zeros, a quick look at the fundamental theorem of algebra, and the conjugate zeros theorem. First, let's look at the definition of a complex number or a complex zero. A complex number can be written in the form a plus bi, where a and b are real numbers. I, which is called the imaginary unit, is equal to the square root of -1. And I squared equals -1. You square it. That's the only time you get a negative number when you square a number. Real number squared, you either get 0 or a positive number. We can say that a is the real part and b is the imaginary part, which is associated with the imaginary unit I. And if a equals to 0, in other words, the real part over here is 0, and b is not, then we have a pure imaginary number. So a pure imaginary number would look like this, say 2i or minus 5i. The real part is equal to 0. So when I write a plus bi, and we say by definition that's a complex number. So if you have 2 plus 7i, that's a complex number. Now notice I can write 5 plus 0i, and that's equal to 5. So the set of real numbers is contained in the set of complex numbers. So when I use the word complex number, I could be talking about a number like 6 or 5 or 3i, a pure imaginary number, or the standard look complex number 2 plus 7i, and so on. Now we can represent a complex number as a vector in more advanced math, but here we're going to say pretty basic. Also, I want to point out to you, if you have a plus bi, standard form of a complex number, then a minus bi is called what we name the conjugate. So 3 plus 5i and 3 minus 5i would be conjugates. Or for the pure imaginary numbers, we could say then 3i and minus 3i are conjugates. Now there is a theorem concerning conjugate zeros, and that simply states that if you have a polynomial with real coefficients, it can't have any complex or imaginary values for coefficients, but if it has real coefficients and you have a complex number, say a plus bi, that's a 0 for that polynomial, then the theorem tells you that the conjugate, or a minus bi, is also a 0. And of course, the fundamental theorem of algebra simply states that if you have a complex polynomial, that is one that could have coefficients that are complex numbers, if it's at least degree 1, then it's going to have at least one complex 0. So that's all this theorem states. If you have a complex polynomial of degree n, where n is greater than or equal to 1, it's going to have at least one complex 0. So let's look at this first problem here. Or find the remaining 2 zeros of a polynomial of degree 6, whose coefficients are real numbers. That's the theorem. This is called the conjugate zeros theorem. So it's degree 6. So if it has degree 6, we expect 6 zeros. They could be repeated. But there you have 1. 2 is a 0, it tells me. -3 is a 0. Now 2i is a 0, so I know that the conjugate, or -2i, is also a 0. 1 minus 2i is a 0, and because the polynomial has real coefficients, then the conjugate of that, which is 1 plus 2i, is also a 0. So find the 2 remaining zeros. Well, right there. So you got 1, 2, 3, 4, 5, 6, and that's what we expect because we have degree 6. Now let's look at the next one. It says find a polynomial of degree 5 whose coefficients are real. So notice coefficients are real. that has zeros of, there you have it. So let's set up this polynomial. So we got 1 0 of 0, so x minus, that tells me then that x minus 0 has to be a factor, so that's just x. Notice I know that minus 2y is a 0, so that tells me that 2y is also a 0 by the conjugate zeros theorem. I'm given that 2 plus I is a 0, so I know that 2 minus I is also a 0. So I gotta have 5 because it's degree 5. So x minus 0, that's 1. Okay. And then I have 2y is a 0, so x minus that has to be a factor. So I write this out. That's one factor of the 5th degree polynomial. Negative 2i is a 0, so x minus that, or x plus 2i is a factor. And then for the other one, I got this one here, x plus 2i, and x minus 2 minus i. So I've got x minus, to the first one, 2 plus i. So let's write that as x minus that. So if I minus that, that'll be a minus 2, and then a minus i. And then 2 minus i is a 0, so x minus that number has to be a factor. So I can write this as x minus that, so that'll give me a minus 2, and x minus I is plus I. So get this. And then this will be x, or x minus, say a minus b, and a plus b, that's a squared minus b squared. So if I multiply these two out here, it'll be the x and the x squared, or multiplied, so give me x squared. And it'll be minus 2i and 2i, so that'll give me a minus 4i squared. But remember, by the definition, I squared is negative 1. So this is plus 4. Now let's break this up into two terms. So let's call that one term, and this another term here. So it's like a minus b, and a plus b is just like I did in this one here. A squared minus b squared. So in this case, it's going to be x minus 2 squared. Let me write it like this. Minus, then I times I is I squared, but I squared is negative 1. Got a minus 1, so that'll be a plus 1 here. So then I just write this as x, and then it's x squared. I'm going to multiply this out. So x minus 2 squared, we multiply the x squared, we square the x, and then it's minus 2 times x, double that, that's 4x, and then minus 2 squared would be the 4, and then of course the I squared here gives us a 1, so 4 and 1 gives us 5, so this is plus 5. And of course I had the x squared plus 4 here, over here. So the polynomial that's generated from these zeros is going to be x times x squared plus 4, and then we have the x squared minus 4x plus 5. This is a square here. So it's x times parentheses x squared plus 4, and then parentheses x squared minus 4x plus 5. And you could multiply those out, but as long as you simplify by eliminating the I, doing the multiplication, using the fact that when you have an I squared, that generates a negative 1. We eliminated the I. And that's just one case here. I could actually multiply this by a constant, and that would give me another polynomial that satisfies this condition. So sometimes they just put a constant and say, okay, put an a in front, where a represents any non-zero constant, and that would be 1. General representation. You can get a polynomial, pick an a to be 1, pick an a to be negative 2 or 3. This is just a general solution here. And the third one, we're looking for the solution to this. Find the complex zeros of the polynomial. So just pretend this is an equation, and I want to know what values make this 0. Well, from the last video on the rational zeros theorem, we know that if a polynomial has a rational 0, it's going to come from factors of the negative 3. So it's going to be either plus or minus 1, plus or minus 3, divided by factors of the lead term. So that could be plus or minus 1, plus or minus 2, So the possible rational zeros we could have are plus or minus 1. I can divide plus or minus 1, plus or minus 3 by these factors. I just get a plus or minus 1, plus or minus 3. Then divide by 2. I'm going to get a plus or minus 1/2, plus or minus 3/2. So what I do is I try to find at least one rational zero and use synthetic division and get the rest of them. So I got, it's 4, 3, 2, 1, and constant. So I already had it in descending power, so I simply use the coefficients. If I have any missing terms, I fill it in with a 0. In this case, no missing terms. So I have a 2, minus 5, a minus 1, another minus 5, and a minus 3. So I select from this list over here, possible zeros that I could have are these right here. Doesn't mean they're going to be zeros, but if we have any, it's going to come from these. So I tried a 3 here, brought the 2 down, and then multiply 3 times 2 is 6. Add, I got 1. 3 times 1 is 3. Add, we get 2. 3 times 2 is 6. 5 minus 5 and 6 is 1. 3 times 1 is 3. Bring it over. I got a 0. So that tells me that the remainder would be 0, which means that 3 generates the factor of x minus 3, or another way to say it is 3 is a 0 of that polynomial. Then you would try it again in case it repeats, but it doesn't. So then the next one that works is 1/2, or minus 1/2. This is trial and error here. So minus 1/2. Bring this down. 2 minus 1/2 times 2 is minus 1. Then at this, you get 0. Multiply. Minus 1/2 times 0 is 0. And we get a 2. And there we go. Minus 1/2 times 2 is a minus 1. At this, we get 0. Add a 0 and a 0. So I got a 0 at the end there. So again, minus 1/2 and 3 are zeros. Notice these complex zeros. Because like I said, a complex number or complex zero includes the real numbers and of course your standard imaginary numbers with the I. So the complex zeros are going to be 3, negative 1/2, and then from this one here we did 2 divisions here, so this is a quadratic here. So the lead term here is an x squared, so it's 2x squared plus 0x plus 2. We want to know what are the zeros for this one. So in this case, the easy way to do it is just set it equal to 0 and solve it for x. 2x squared is equal to negative 2. So x squared is equal to negative 1. Notice I have a square number equal to a negative. You know that this has to be a pure imaginary number in this case. So take the square root plus or minus. So it'd be plus or minus the square root of a negative 1. That, of course, is your I. So this is plus or minus I. So these are the complex zeros. 3 minus 1/2 plus or minus I. Thanks for watching. We'll see you next time.